I declare no conflict of interest. Most of my work has been supported by NICHD, including the time that I spent with George. I also need to thank my family, who are the ones who got me into this field. My husband, Steve Porges, and my 2 sons, and a long list of collaborators. I'm going to not be able to give everyone the credit they deserve because of time. I'm going to ask questions that were brought to me, not through my own intention. I was studying social bonds. I was told by the media that this was love, and I spent a lot of time trying to explain how that wasn't the case. But I was wrong. I was studying love, and it's something we're all interested in, I think. But we have to define it as a scientist would, and then to talk about what kinds of biology underlies love. Attachment and bonding are 2 other concepts that we use. I was studying social animals that formed pair bonds. I sort of walked accidentally into an interesting molecule known as oxytocin. Everyone here knows oxytocin, but you've also experienced it because you're mammals. And this will help us to understand the role of love, social bonds, social support, and nurture in both mental and physical health. I'm going to ask, how does receiving love in early life allow us to give and receive love later? We all know that this is true. We have only now just begun to understand how it works. How does love protect and heal? It does. And then I'm going to talk about a few mechanisms, physiological and epigenetic, through which social experience, including early life nurture, love in early life, or its absence, can influence health across the lifespan. Love is usually defined by at least one common feature: social attachments and social bonds. Here, I'm going to talk about a complex of neurobiological processes that facilitate health, wellness, reproductive fitness, and biological optimality. Now, to understand love, we have to realize its context. It's about survival and it's about reproduction, both of those. The evolutionary prototype is the mother-child interaction. Birth, lactation, and maternal behavior are important natural models for studying the neurobiology of love and the functions of oxytocin, what some people call the hormone of love. It's important always to realize that humans could not have existed without oxytocin because we are breastfeeding species. Historically, it was the only way to nourish a baby. It might not be the mother, the biological mother, but somebody had to provide human milk for babies. We also know there's a biochemistry in this story. I don't know if you can see, I love this slide of Lavoisier and his wife because it shows both chemistry and love in the same picture. Social bonds, the biology of love, appears in association then with birth and lactation. And I'm going to tell you a little bit about the molecule. I'm sure you've all seen or had some exposure to the chemistry. It's a simple 9 amino acids configured as a ring and a tail. But oxytocin's also, that one molecule, is the central element in social attachment and love. Now, there is something here just for George. Would you help me read this? This is a correspondence between myself and Roger Guillemin. Some of you will recognize his name. He is one of the fathers of this field. He received the Nobel Prize for his work in the discovery of GnRH, one of the 3 at that time. And he heard me talk and show that picture of Lavoisier, and I guess it kind of drove him crazy. He said, something's wrong. He said, Lavoisier was using the word OXY, oxygen, to mean sharp generating. But how did oxytocin become to mean sharp birth? And he thinks, and you can tell me if this is correct, that a mistake was made in the translation and that it should have been Ocytocin. Now, those of you who are French can feel very superior at this moment because the French language never gave up the incorrect spelling. Roger tried to understand it, and there's a little joke on here I won't have time to tell you, but he's been searching ever since, and he's like 95 years old, to find out who made the mistake. But the Oxford World Dictionary accepts it as it is, so we will go on calling it oxytocin for today. Oxytocin was classically viewed, as you all know, as a female reproductive hormone acting on the uterus and the mammary gland. This got it into trouble right from the start, because if something was only about females, why bother to study it? And I am not being feminist or facetious, it just was considered some oddball molecule that didn't affect at least half of the world. Of course, they were wrong about that too. So actually, I'm writing a paper on all the things that have been misunderstood about oxytocin. It's 10 pages of mistakes so far. Oxytocin does affect both males and females, and it doesn't just work on the uterus and the mammary gland. It works throughout the body, but it is made, interestingly enough, primarily in the brain. And then released, classic story is it's released into the blood at the posterior pituitary, but it's also released, as those arrows are trying to indicate, it's released into the brain itself. Oxytocin affects not only social behavior and social bonds, but it affects, and I'll say this several times, the autonomic nervous system, the HPA axis, which is some of the work we did with George, and the immune system. And basically, it's an adaptive molecule. It allows the body to adapt and heal itself, especially in the face of challenge. I don't have a slide for this, but the conversations I had with George over all those years, I kept saying, George, why are we not dead? If stress is so bad, what's keeping us alive? And I was struggling for something, something of value and important, because we do survive amazing amounts of stress. And I think one of the answers is oxytocin. It's central to the biology of social behavior. That keeps us alive, bonds, social support, sexual behavior, and I would argue, I wrote a long discourse on this, that it also permitted the evolution of the human nervous system. The human nervous system, of course, started historically. Mammals were evolved from simple primitive reptiles. Oxytocin allows that transition from reptile to mammal. It permits birth. It isn't essential for birth because other molecules are involved, but it expels, in the human, it's probably especially important because of our big heads. We have to get out of the uterus. It's a considerable task to cause the muscle contractions that are needed for human birth. And oxytocin permits post-birth nutrition. It supports the baby both physically, nutritionally, but also behaviorally, and because of its role in the autonomic nervous system and in the vagus, it helps myelinate, it allows oxygenation, the myelinated vagus. It's necessary to get oxygen to this massive brain. It permits human cognition and social behavior, and I would argue we are here today because of oxytocin. Now, oxytocin's effects also allowed us to have this complex cognition that humans call love. We had special problems in birth because we have a big cortex, a skull to protect that cortex, bipedal locomotion, a small rigid pelvic girdle, unlike the gorilla, which can walk on all four legs, and we simply had to have oxytocin. Oxytocin's extremely difficult to work with, and it's difficult to measure, and I'll share with you why I think that's the case. For one thing, it can change very quickly. This is an example done by someone I work with in salivary oxytocin measuring as a function of orgasm. So the 0 there is the orgasmic experience. You see it hit its peak at about 10 minutes and then went down very quickly. Rose to a very high level, picograms per ml. There are people wasting their time worrying about the amounts of oxytocin. There's a lot. Okay, I'll use a technical term. But here's the problem. Oxytocin is found free, only for a few minutes probably. This is a model from one of my collaborators, Lance Martin. It begins quickly to be, it has 2 sulfur bonds, and this binds it to other sulfur-containing molecules. And over time, it will go to the receptor and make covalent bonds, and any number of other interesting things can happen. So it's a dynamic, changing creature. It's not one simple 9-amino acid. However, the main thing that we need to understand is not the peptide itself, perhaps, so much as its receptor, which is a transmembrane G-coupled protein, the receptor is, and it is found throughout the body, not only in the brain, where it's quite abundant, but also in the autonomic nervous system, immune system, even the gut. The autonomic nervous system, as I mentioned, has many targets. It's full of oxytocin receptor, and almost every organ, I would say all of the organs, are sensitive in one way or another to oxytocin. So many of the effects of oxytocin on emotions and what humans call love are actually autonomic effects. You feel them in a very vague way. They're hard to explain because they're not discrete. And then the converse occurs. Love affects the entire body. So oxytocin allows us to feel love, and it also allows us to respond. Our work in voles and humans showed that oxytocin can be released under conditions that involve positive social interactions, especially if in a context of safety. Pair bonding, maternal behavior, paternal, males release oxytocin, at least the little rodents here, and sexual behavior. Oxytocin is a neuropeptide. That's how it's usually described. Sometimes we'll talk as a neuromodulator, made primarily in the brain, released into the brain, but it also gets into the spinal cord. And it is probably, I would argue then, in sort of summary on this point, a major factor in our capacity to protect or heal in the face of challenge. But it can also heal directly, and there are these magnificent studies coming from all over the world showing that injured skin, cardiac infarct, osteoporosis, intestinal bowel disease, stroke, mental disorders, all of these can be improved in some way if oxytocin's acting normally. It's anti-inflammatory and it's antioxidant. And again, working with George, he was really one of the first people that I dealt with who was so engaged with the anti-inflammatory effects of molecules, and oxytocin is one of those. And of course, it's even been shown to be necessary for the effects of probiotics, such as Lactobacillus reuteri. I'm not going to show you the data because we don't have much time. I do need to help you understand that oxytocin does not work alone, and its primary sibling is vasopressin, from which it only differs by 2 amino acids. And that provides very interesting opportunities for interaction. Now, vasopressin's the older. It's considered to be around 200 million years old, evolved from a similar molecule called vasotocin. Oxytocin appeared about 100 million years ago, at about the time that mammals evolved. We don't know which is cause and which is effect, but it is during this transition from reptile to mammal that oxytocin became important. Vasopressin is adaptive, very adaptive molecule, permits the defense of self and others. It's part of the HPA axis. It's involved in vigilance, hypermobilization, usually, not always, territoriality, sympathetic nervous system arousal, and even fear. Male-male aggression in animals, in this case the prairie vole, is regulated by vasopressin. Oxytocin is also released under stress. People have come to me for years trying to get help to measure oxytocin because they thought, well, low oxytocin bad, high oxytocin good. But in fact, the times when you can see most clearly high levels of oxytocin are when something bad has happened. Forced restraint, immune challenge, chronic isolation, only in females. And at high levels, oxytocin may actually act as if it were vasopressin. So anyway, a brief summary here of vasopressin's effects: fear, defense, territoriality, vigilance, arousal, mobilization, sympathetic neural effects, and protective active strategies. Oxytocin allows us as mammals to have another strategy, one where there is sociality, sharing, civilization, I left that off, relaxation, resilience, immobility without fear, and the parasympathetic nervous system, although both oxytocin and vasopressin are involved in both of those autonomic systems, and these direct healing effects, especially, again, when there's a sense of safety. So the problem with studying a molecule like this is that context is everything. And love and safety allow oxytocin, I believe, to permit social bonds and allow us to feel safe or calm. Vasopressin, again, in a context of anxiety or fear, gives you pretty much the opposite effects. Now, for the last few years, papers have come out, numerous papers, talking about paradoxical effects of oxytocin. In fact, I don't think they're paradoxical at all. Nothing in science is ever truly paradoxical. What we have instead is a system that under certain conditions acts on the oxytocin receptor, and under conditions of anxiety probably acts on the vasopressin receptor. So it acts as if it's vasopressin, and this has made it very difficult to study. I think I'll just explain briefly that different amounts, I won't go through this slide, it's complicated, but a basic argument is that when oxytocin's dominant, we can survive all kinds of things, trauma, stressors, whatever. If that system gets shut down, and it can be shut down by life experiences, then vasopressin takes over. And we see the world differently, not through the eyes of love, but through the eyes of fear. And there is a sex difference. We don't have time to tell that story. But these two molecules are in a constant dynamic dance. Both are critical for health, oxytocin especially for synchrony and safety, interacting with others. And when both are working in a sort of optimal way, oxytocin and vasopressin and their receptors, we can be engaged in selective sociality. Oxytocin alone or vasopressin alone actually it encourages a different kind of response, and those are usually not selective. And selectivity is at the heart of what we humans call love. I know there are people from certain religious traditions who use the word in different ways, but I'm using it in the context of human selective bonds. So the Bible says there is no fear in love, but love casteth out fear. Love overcomes fear. It's one of the few tools we have to bring ourselves out of a state of fear. Now, as I mentioned before, this is a chemical process in my mind, or a neurochemical process, and it's most easily studied in animal models. The emotions and behaviors associated with love, social bonds, social support are not limited to humans, and these core studies are most easily done in rodents, where we can work quickly, and I happen, through sort of good luck, to come upon a creature known as the prairie vole. It's one of perhaps 3 to 9% of mammalian species that have been called monogamous. These animals happen to depend very heavily on oxytocin and vasopressin to run their social lives, and to a much less extent on steroid hormones. And I don't have time to tell you that story, but basically it turns out they're a kind of demasculinized species. Prairie voles can be studied in nature and in the laboratory, and they have given us new information on everything I've talked about today. This very interesting process, the part of it that I'm particularly interested in at least, is the early life experience. How does early nurture act on these systems to protect us across the lifespan? And basically it does. The peptide receptors give us some of the answer. These pictures were from Socia Wong, who was a postdoc with me years ago. And what we found is that by studying different species, not just prairie voles, but a related species, we can see different patterns of receptors. This is a prairie vole, a slice through a prairie vole brain. This is a montane vole, very similar to look at from the outside, but internally using peptides in different ways. The prairie voles, at least in this section, have high levels of oxytocin receptors, lower levels of vasopressin. The montane, the non-monogamous, less social mammal, less oxytocin, more vasopressin. So that's kind of nice. We've been working on this in several ways. One is to look at the autonomic function, and what we found was that prairie voles have a human-like parasympathetic nervous system. This was pretty shocking. We did not expect a rodent to have a high level of vagal tone. Their heart rate can be rapidly dropped, just as in humans. They also share with humans the ability for early life experience to epigenetically regulate the oxytocin receptor. This is probably true of many mammals, but it's especially easy to study here. The team of researchers that I've worked with on this, especially Jessica Conley, who's an epigeneticist, Alison Perkabile, and Will Kinkle, both of whom are postdoctoral fellows or were with me, and of course the prairie voles themselves. And what they showed us was that the effects of oxytocin could be seen as a manifestation of different kinds of early life experience. So what happens is that via oxytocin, early life experience affects the oxytocin receptor, so it feeds back on itself. This, in turn, regulates the effects of oxytocin, modifies social behavior, and I would say stress reactivity across the lifespan. So the prairie vole is an excellent model for discovering mechanisms of early experience, and what we have found, and there are many experiments, some of which are coming out in press right now, showing that early life experience can literally tune the oxytocin receptor via DNA methylation or silencing of the receptor gene. Novel methods came from Jess's work. She had done this in humans first, in autism, and we also did studies in postpartum depression, which came out in 2015. What these show is that high levels of methylation, which our animal work shows is associated with low levels of oxytocin receptor, leave you unable to manage many kinds of social stress. This epigenetics allows the body to be retuned by experience and respond to oxytocin differently. I won't probably take the time to go through exactly how this works, but what's amazing is that prairie voles have what are called CPG sites in the promoter region of the oxytocin receptor that are identical to those found in humans, rats and mice. Mice have one of these Rats do not have any. So it's possible, this is pure speculation, that these highly social mammals are using that epigenetic mechanism differently than less social mammals. Okay, we did experiments to look at this by altering early life experience, a simple manipulation of handling animals on the first day of life, and then measuring the site-specific DNA methylation 24 days later. So one quick manipulation led to differences that could be detected in two different brain regions and at different CPG sites. Handling increases parental response to the babies. This reduces methylation and increases the oxytocin receptor. So the differences can also be seen in natural variation. You may be familiar. The beautiful work of Michael Meany and his collaborators on the HPA axis. That work focuses on basically glucocorticoid system. This oxytocin effect has many parallels. The variation then can be a matter of turning off and on the receptor by early life experience. Epigenetic markers can be affected then by postnatal experience, and these can either prevent or perhaps enhance methylation. We're finding both directions can occur. I'm not going to take the time, we're running short. What I would like to do is say that oxytocin exposure epigenetically programs the developing nervous system and subsequent behavior with effects that are due in part to changes in the gene for oxytocin and the oxytocin receptor. High doses, however, it's like everything else in life. More is not always better. High doses of oxytocin actually given in early life can disrupt social behavior. They may alter methylation, and they may also work on the vasopressin receptor and probably any number of other things. The effects of oxytocin in early life are age-dependent. Early life, we all know this, early life matters. The world of the pediatric endocrinologist is totally devoted to understanding that, how important early life is. And we have found over and over again sex differences. I think this is because of androgens and vasopressin, which is spelled wrong. And the effects, however, for early life experience are much more obvious in males. This is male prairie voles, but I think it applies to humans as well. So oxytocin epigenetically programs the developing nervous system and subsequent behavior. The sex differences component of this seems likely to be due to the fact that androgens, they don't disrupt oxytocin's effects, but they modify it in ways that we don't understand very well. We also have a problem because you can't just give more. You have to find, and we haven't done this work, exactly what is the optimal biological range. High doses seem disruptive, possibly because they actually increase methylation with effects that are more apparent in males, and the early effects of early experience are different. This tuning is part of a study that I started, 2000, long time ago, trying to understand the effects of Pitocin. So as you all know, we're involved in one of the largest human experiments in history, in which babies are delivered often with extra oxytocin or Pitocin on board. In prairie voles, this is not good news if there's too much. Okay, it inhibits pair bonding, other aspects of behavior. Low doses don't do that. So I'm not saying all extra oxytocin necessarily bad, but I can be pretty confident that no one has carefully gone through what's the right dose in humans based on the kinds of dependent variables I'm interested in. They're much more concerned about how long does the birth take, or is there a mortality or a morbidity. C-section alters oxytocin. If you don't go through a birth, you don't have the same effects. So what I would like to say is, although Pitocin, some people have argued, it's the most abused drug in the world today. It's also a drug with effects that mimic those of what we've called the power of love. How does it work? We don't understand it too well. We know it originates in birth. I would argue we should give Mother Nature some respect and become more involved and more informed before we manipulate her power. And I end with a quote here from Marie Curie. "Nothing is to be feared, it is only to be understood. Now is the time to understand more so that we may fear less." Thank you.